Alright, welcome to a new lecture. This time we're going to talk about a wonderful concept called data representation, which we have seen before. It's like binary and all those different bases and things, so we'll review those things and go a bit further, because why not? Alright, so this kind of stuff is talked about in Chapter 4 of your Dive into Systems book, so please go and read that next, alright, after you're done with the other stuff. I guess let's get right on into it and start with bases and base conversion. So this should be a review. I teach this in 40 for sure, and 26 if you've taken that already. So let us remember all these different bases that exist and the ones that are important to computer science as well. Okay, so yeah, as humans, we like to use decimal numbers when we're writing stuff out, right? Let me fix my pens really quick. Is that already fine? No, it was, and then I messed it up. So as humans, we like to think of things in terms of decimal numbers or base 10 numbers. And so like the normal numbers that we write look like this, 123, right? And that is secretly in a certain base, it's base 10. So I can put a subscript there to specify this time. And decimal numbers or base 10 numbers, they're made up of, they're like a string of digits, and the digits we get to choose from in base 10 are a set of size 10. So we have 0 as a digit, 1, 2, all the way to 9. That's 10 digits total, and that's what it means to be a number in base 10. You have 10 digits total to work with. The second you want to add 1 to 9, you need a new place, right? So yeah, let's remember that elementary school stuff of like breaking down decimal numbers into their places, because that's going to become important when we have more than just decimal. So here is 1,234 in decimal, the number that we know and love. 1, 2, 3, 4 base 10. We know how to break that down, right? 1,234. In elementary school, we learned that that's 1,000 plus 200 plus 30 plus 4, right? And then once we learned exponents, maybe in middle school, then it was 1 times 10 to the 3 plus 2 times 10 squared plus 3 times 10 to the first plus 4. You can also have a times 10 here, but it's times 10 to the 0, all right? And do we see where the base appears again? All right, so here it's always powers of our base, and that's how we form numbers in decimal, right? That's the secret. So there's always going to be a power of a base, excuse me, for every digit, okay? And so that's how we can break down decimal numbers. There's actually an algorithm for that. If you didn't have the number in front of you, if you had it sitting inside of a computer, you can turn your number, if it's just a black box, think of it as that, you can't see all of its digits, you can extract the decimal digits from a decimal number by repeatedly doing integer division and then taking the remainder, doing that modulus operation. So let's break down again 1,234, and I'll show you the algorithm, right? Because this will apply to other bases as well. So 1,234, there's a way to break it down into its corresponding digits, and you work your way in from the right, right? So the way to extract this 4 from 1,234, if you didn't know that that was the full number, you would do mod 10, do remainder after dividing by 10 first, and that would give you the 4, right? Because it goes in 123 times with 4 left over. That's perfect. That would give you the 4. And then, if this is how we can always get the rightmost digit of any decimal number, then how can we, if we could only just turn this into 123, if we can go from 1,234 to 123, then I can play the same game and get the 3 out, and then the 2, and then the 1. So, do you see the secret? It's the other operation I just said, right? It's if you do integer division by 10, that's 123.4, but you chop off the 0.4, that gives you 123 to work with. So modulus and division will extract all the digits for you. So now if we want the 3, we just take 123 mod 10, that'll give us the 3, right? Because it goes into 10, 10 goes into 123 12 times with 3 left over. And then if you want to chop off the 3 and turn it into 12, you can again integer divide by 10, and that will give you 12. And now you just do the same process on that, extract both of its digits. So 12 mod 10 gives you 2, extract that one, turn the 12 into 1 by integer dividing by 10. That gives you the 1, the final digit, and then say you're not sure, this is an algorithm, we're not sure if we're done yet, we don't know what number we have yet. Do mod 10 to extract the rightmost digit of 1, which is just 1, goes in 0 times with 1 left over, and then we do it one more time. Let's shift away that 1, let's chop off the 1 by doing integer division. 1 integer divided by 10, 0.1, right? And so it's 0. And that is the algorithm. Once you hit 0, you know that your number is finished and you've extracted all the digits. And so do you see, first of all, where the base appears? That's important. The base is right here, all over the place. That's great. So every time you take a modulus, you get a digit in reverse order. See that? So every time I took a modulus, all these places, I got a digit, but in reverse order. So it's 1, 2, 3, 4. Those are all the digits of my number if I didn't know otherwise. All right? And so that's perfect. If your number was a black box, you couldn't see it, it was in memory somewhere, you didn't know when it was finished, you can keep playing this game with it as long as you could do modulus and division. And once you know it's 0, then you're done. All right? So that is the secret. And of course, the whole reason I'm talking about this is because there's more bases than just decimal. We care about binary in this class. We care about a lot of different bases that are powers of 2. But let me teach you this for arbitrary bases. All right? So let's say that I give you a number that's not in decimal. So this is 234 base 7. All right? That's pretty nice. Remember that base 7 numbers, a number in base 7, which digits does it have to choose from? Digits in base 7. That is all the numbers, 0, 1, 2, all the way to 6, right? 7 digits total. Second, you want to add 1 to 6, you got to add a new place in base 7. So yeah, converting any number in a different base back to decimal that's the easy way, which is nice for us. So let's say I give you this number 234. It's not 234, sorry. It's 234 base 7. Let's convert that to base 10 by doing not the base 10 expansion like this was, but the base 7 expansion. And then once we do the math, we have the answer. All right? So just like you can split up this number into corresponding powers of bases, like starting with the rightmost, like this is 4 times 10 to the 0, this is plus 3 times 10 to the 1. The whole game applies for base 7. So how do we convert this? Well, it's going to be start with the rightmost digit, 4 times 7 to the 0, plus 3 times 7 to the 1. Does that make sense? So that's going to be, this is now the 7's place, which is interesting to think about, plus 2 times 7 squared. That's the 49's place, which is also fun. So again, the base appears right here, and if you do the math, for fun, we'll do it together. Whee, Python. 2 times 49 plus 3 times 7 plus 4. That just so happens to be 123 in decimal. Cool. And we'll use the subscript to specify. Okay, so that's how you convert a number to decimal. And we're following this process. The other way involves this kind of algorithm, and that's harder. If you want to convert a number from decimal, you have a number in decimal right now, and you like to convert it to a different base, like base 7, that's the hard direction, sadly. You got to do all this stuff. Okay, but again, it's not too hard once you wrap your mind around it. It's just going to be put the base you want right here, and then you'll be extracting that base digits every time you take a modulus. Okay, so all the stuff that I just showed you will apply, which is nice. All right, so let's convert 123 base 10 normal number that we know and love to whatever it is in base 7. We do know the answer right now. It's going to be this one, right? So let's make sure, let's confirm that it's going to work. So again, base 7 digits look like this. You only have these to work with. 3, 4, 5, 6. Those are all the digits you get. The second you want to add 1, right, in base 7 to the number 6, which is the last single digit. Well, that must be, you have to add a new digit, right? You have to add a new place. So this is always... that is always the base, right? So 1 0 in decimal is 10, which is the same as the base. 1 0 in base 7 is 7, which is always the same as the base. So we're going to do this process, but it's going to be mod 7 integer divide by 7 this time, okay? So Yeah, let's start with 123. We know how to do math in decimal, which is nice. We're just going to do mod 7. And what this will do is extract the base 7 digit from 123, the rightmost base 7 digit. I hope that makes sense. And as a sanity check, this makes sense, right? Because mod 7 is only ever going to give you an answer that's one of those numbers. So that's perfect. So 123 mod 7, if we didn't know already, is 4. That's the rightmost digit, all right, in base 7 of 123. And now let's chop off that 4 in base 7 land by taking 123 and doing integer division by 7. So again, this process all over again, just in base 7. And that will give us the new number to extract all the base 7 digits of. All right, in Python, it's 2 slashes to do integer division. So it's 17. All right, so now it's 17. If I can just convert that to base 7, we're home free. So 17 mod 7, get its rightmost decimal, or rightmost base 7 digit. 714 goes in twice with 3 left over, as we expect, right? Because we do know the answer secretly. And all right, let's extract that 3. Let's chop off the 3 from the base 7 representation of 17 by doing 17 integer divide by 7. So the answer is 2. All right. And then we'll extract the rightmost base 7 digit of 2 by doing 2 mod 7, which is just 2 because it goes in 0 times with 2 left over. And then we'll chop off the 2 from this number and see what we have left, see if we're done yet. And that'll give us 0 in integer division land, and that's how we know we're finished. All right, so every time we took that modulus, we got a remainder, that gave us a digit in that base we were trying to convert to, which is base 7, in reverse order. So the answer is 234 base 7, and you can always check that by doing this. All right, so that's the answer. That's how you find it. That's how you convert to any base under the sun. Okay, we care about binary, of course, in this class. That's base 2, and we get 2 digits to work with, right, in each place. So all the digits you get in binary are 0 and 1, which hopefully makes sense. And so numbers look kind of like this in binary, base 2. In computers, because we are computer scientists, we like to program, there's a way to enter a binary number straight into C++, for example. If you can't really do a subscript in programming inside of a text editor. So instead, they've done this. They've said 0b. If you start a number with 0b, that means, in C++ at least, whatever you put after that is to be interpreted as a binary number. All right? So that's how that works. And yeah, every binary digit we call a bit, because we just shorten the word, which is cute. And so this is a 4-bit number, and it takes space. It takes 4 bits of space to store it. So that leads naturally to an idea of space and storage. Yeah, since we only have these digits to work with, 0 and 1, that means 1 plus 1 in binary, the answer is 2. You need to add a new place, right? 1, 0, because you've run out of digits. So this is the number 2 in binary. You add 1 again, the number 3 is 1, 1. So that's how that kind of works. And yeah, 8 bits make a byte. We care a lot about bytes in computer science. Every integer is 4 bytes long, for example. Megabytes, gigabytes, stuff like that. The smallest byte is 8 zeros. The largest byte is unsigned, at least. The largest byte is all ones. Okay, that's how that works. And maybe you haven't seen this before. You can totally do math in binary. You just have to remember to like carry a bit sooner, because you like the number 1, 0 is like that. Or is the number 2, 1 plus 1, you have to carry 1, 0. So let me show that to you. So here is let's do 1, 0, 1, 0 base 2 plus 1, 1, 1, 1 base 2. What's the answer? So it is just like normal addition until you have to carry. So 0 plus 1, that is 1, and we can fit that into binary digit land. That's fine. And then 1 plus 1, though, that's 1, 0. We need to add a new place. So 1, 0. So we carry the 1. And again, 1 plus 1 is 1, 0. And then 1 plus 1 plus 1, which is 3, that's 1, 1. All right, so we carry a 1 out here, and then also put a 1 here, and that carried 1 ends up over here because we're done now. So that's how that works. All right, and we can check that, we can check our work by doing this. We can say, okay, 0b also works in Python. 1010, that's the number 10 in decimal. 0b1111 is 15. What's 10 plus 15? It's 25, of course. 0b11001, which was the answer we got. Ooh, that worked out. Good job, us. Cool, huh? So, yeah, that's binary. Other powers of 2 bases are also important to us. Octal is another one. That's base 8. The digits you have to work with in octal. Of course, it's called octal because it's base 8. 1, 2, all the way to 7. Those are your digits you get. And so, I guess, octal numbers, they kind of look like this. 63 is a valid octal number, but inside of a computer, if you wanted to type this, programming languages let you type numbers in octal form, even if you haven't seen that before. I promise it's useful sometimes. So this octal number, if you wanted to type that in, 63, base 8, in languages they let you do it this way. Either it's 0O, just like 0B, to specify this is a base 8 number. You should interpret it that way. It's not the number 63. It's smaller because it's base 8. Or if you start a number with a 0, that should signify that it's meant to be interpreted as octal as well. So certain languages let you do it this way, certain languages let you do that way. I honestly forget which one is C++. Honestly, C++ might let you do both. So try it. Try it and see. Yeah. The nice thing about bases that are powers of 2, like base 8 is 2 to the 3rd power, you can go in between it and binary very, very quickly. All right, because every octal digit, a single octal digit, corresponds exactly to 3 bits. And let me prove that to you. So the octal digits are 0 through 7. If you use 3 bits always, 0 through 7, 7 of course in binary is 111. You see how that's the biggest 3-bit number. If you just always remember to translate over and use 3 bits even if you didn't need to, like for the digit 0, every single octal digit corresponds to a 3-bit number, which is nice. So you can just read it off. So for example, this number, 110 in binary, 110011, in octal you can just read it off because you can be like, all right, this 3 digits corresponds to the number 3 in octal because it's 1 plus 1 is 3. Or sorry, 2 plus 1 is 3. Just convert that to that. And then the 110 corresponds to, that's 4 plus 2, so 6. So 6, 3, you can break it down just like that. All right. So I hope that makes sense. And if you want the real proof of that, it's like, all right, the blue stuff, it corresponds to these things. That's how you can do the base expansion in binary. You can factor out a 2 to the 3rd power from all these. And you can factor out a 1, of course, from these. And 2 to the 3rd is 8 to the 1st. Hoo-hoo. So now we're trying to go backwards, right, into octal land. And 2 to the 0 is the same as 8 to the 0, of course. So this can all be... you can draw some parentheses and translate it into 6 times 8 to the 1st plus 3 times 8 to the 0, and that's your octal number. Okay, so you don't have to prove it to yourself if you want to take my word for it, but you can just like read them off, and you can go backwards too. It's like, all right, the 3 corresponds to 011, 3 digits, and the 6 corresponds to 110. Bam, call it a day. You're done. All right, so that's octal, base 8. Hexadecimal is another very important one. That's base 16, of course. So this one's fun because you get extra digits now. So base 16 means you have 16 digits before you need a new place, right? So you have 0, 1, 2, all the way to 9, and then you go after 9 because you have 16 digits to work with before you need a new place. So we started using letters, right? You have A, B, C, D, E, and F. A is the single digit that means 10, B is the single digit that means 11, C is 12, I can't do math and write letters at the same time, D is 13, E is 14, F is 15, okay? And hex for short, inside of a computer, you can type a hexadecimal number by starting with 0x, that works for sure in C++, and again, there's an easy way to convert between binary and hexadecimal, just like there was for octal. So every single hex digit corresponds to exactly 4 bits, if you think about it, like F15 corresponds to 1111. So as long as you just always take your every digit and you translate it into exactly 4 bits, even the ones that don't need it, like 0, then you can always translate very quickly, okay? So that's how that works. And again, I can prove it to you. Let's break this number down in binary. you just go from the right, just draw lines over, or circle every chunk of 4 bits. And so every 4 bits correspond to a single hex digit. So this is the number what in decimal? It's going to be 2 plus 4 plus 8, so 12, 13, 14. And that is going to be E. All right, so that's an E that this corresponds to. E on the right. And what's this? This is 8 plus 2, so 10. And we know that that is A. The hex digit for that is A. And then this one is just 4. And then this one is 8 plus 1, or 9. And that's just the normal hex digit for that is 9. And so to enter that into a computer, you say 0x94AE. Okay? And of course you can go backwards. Just the E immediately, just translate that into 4 bits. The A, translate that into 4 bits. The 4, translate that into 4 bits. You can go back and forth very, very easily. Okay? And as usual, you can do math in these different bases. It is a little weird to wrap your mind around, but it totally works. So let's do these. 4FB. Let me give myself some more room, actually. 4FB plus 1C7, hexadecimal land. So what in the world is B plus 7 is the first question. What do we got to do here? So B, if you forget, you can always just like go to Python and be like 0xB, what is that? That's 11. 11 plus 7 is 18. All right, so 18 in hex is 1, 2, because the 1 is 16, contributes 16, and then 2 left over. All right, so 1, 2, so you carry that 1. All right, so that's how that works, and now we have a new number here to carry. So now it's going to be F plus C plus 1. So 15 plus 14, 13, 12. 15 plus 12 plus 1. 15 plus 13, 28. 0, you can just do it in Python if you want to. 0, that's 15. That's 12. 15 plus 12 plus 1 is 28. And that is going to be, let's see, 2 16s. It's not a, you're not going to carry a 2 here because 2 times 16 would have been 32. So it's going to be a 1 again. What's 28 minus 16 now? So that's what's left over. So 12 left over. What is 12 in hex? I think you can do that. It's C. All right. So it's C there. 1C was our answer. And that was our 28. All right. And you can always confirm that 1C. Honestly, it's a little quicker to do it in Python. You just say hex 28. It would have worked. Would have shown you the full answer. But I want you to see how to think about it. And then 4 plus 1 is just 6. So we're good there. So the answer is 6C2 base 16. All right. In case you're ever stranded and you need to be able to do this. Now you know. Okay. So you try now. I've given you a bunch of different ideas. See if you can remember how to do it. All right, so here is 432 base 10. This is a decimal number. I'd like you to convert that decimal number to all of these, binary, octal, and hex. All 3 of them. Remember that octal is base 8, hex is base 16. Let me go to every slide in between if you want to pause the video and take a look. So 432, convert it to all these bases. Here's your algorithms, right? One or more of these slides will be useful to you. So give that a try. And my hint to you is like, which base should you start with? Should you convert to make your job the easiest? Because I told you can convert in between a lot of things when they're power of the 2, right? So I think the minimum amount of work would be to convert this to hex, because that would be the minimum number of things to do. Because with binary, it'd be 1,000,000 digits long, right? With hex, it would be 3 or less, because the base is just as big. It's bigger than 10. So I'm going to convert 432 to hexadecimal, and that's going to be my starting point. So 432 mod 16, that is what? 432 mod 16 is 0. There's nothing left over. So the rightmost digit in hex of 432 is 0. Let's chop off that 0 in hex land by integer dividing by 16. So 432 integer divided by 16 is 27. And now let's convert 27 to hex. 27 mod 16 is what? I don't know. 11 apparently. And so we have to convert that to a hex digit soon. But all right, 11, let's chop off the 11 out of 27. All right, let's do it now, right? So 11, what is that? If A is 10, that means B. This is really the digit B in hexadecimal. And then let's chop off the B in 27. All right, so 27 integer divided by 16. I think it only goes in once, right? 20, because it's not 32. So 1. Let's convert 1 to hexadecimal, very easy. It's just 1. Let's chop off the 1 to see if we're done. And yeah, that finishes the process. And so every time we took a mod, we got a digit in reverse order. So it's 1B0 is the answer. All right. So that is the hex answer. And then everything else should follow pretty simply. All right. So because I can always go from hex to binary, right? Every hex digit corresponds to 4 bits. So let's take every digit and correspond it to 4 bits. So what's 0 in binary? 4 bits wide. That is going to be 1, 2, 3, 4 zeros. Cool. What's B? We know that that's 11. What's 11 in binary in 4 bits? So that's 8 plus, not 4, but plus 2. That makes 12 so far. No, wait, excuse me. 8, no, yeah. 8 plus 2 is 10, plus another is 11. So that's 1, 0, 1, 1. Cool. And then what is 1 in hexadecimal, 4 bits wide? That's just 0, 0, 0, 1. So that's the answer. That's the binary answer. Okay. And then we can easily go from this to octal, because every 3 bits corresponds to an octal number. We just start from the right, always. Okay. So here, we're just going to circle chunks of 3 bits. That one, that one, that one. And then the zeros don't really do anything, so we don't really need to convert that to anything special. We can just stop. But those are my chunks of 3 bits. And you just read them off in octal now. So convert this 3 bits to an octal digit. All zeros is still 0. This is 4 plus 2, so 6. This is also 4 plus 2, so 6. So it's 660 in base 8 land. And you can always go and check these things. 0x1b0, 0o660, yeah, and 0b110, 110, 000. And they all work. Cool, huh? So I hope you saw like the strategy there, but that is some interesting information, I hope. So let's next talk about representing stuff inside of a computer. Okay, so we have types, and each thing takes up memory, and that memory is taking up a certain number of bytes usually. All right, so every integer, for example, takes up exactly 4 bytes. That is 8 hex digits total, because every hex digit corresponds to 4 bits. There's 8 bits in a byte, and so there's 8 hex digits per byte. All right, so my question to you now, first of all, I hope that makes sense. So this is 4 bits, a hex digit. There's another 4 bits. That's 1 byte long. So every 2 hex digits is 1 byte. All right. How do we think then the computer stores the integer 42? Right? Because 42, first of all, in base 10 is 2a. Base 16. This is a question for you to ponder. All right. So if we have a variable, right, it's sitting at a certain address, like address 100 is where it lives, it holds 42 as an int. It's 4 bytes of that holding 42. How would you store it inside of a computer? Write it down in 8-digit hex form. So your answer needs to look like this. Yeah. How would you do it? What do you think it would look like? Because it's 42. It's 2a, but we have more room than just 2a. Where would you put everything else? Just a bunch of zeros, right? So I think this would be my answer, right? 0, 0, 0, 0, 0, 0, 2a. But unfortunately, things are a bit more complicated inside the computer. You would think then that, all right, if the x lives at address 100, it looks like this. You would imagine this is what would happen, right? And I'm here to tell you it's not like this. So at address 100, you would expect like, all right, dun dun dun, I put a 0, 0 there. Address 101, I'd put another, like you can hold a single byte per address, right? 0, 0 again in hex. Then at address 102, you'd put another 00. And then finally at address 103, you'd put 2A. That would make sense, right? But surprisingly, in modern day computers, that is not how we store 42. You still need the zeros, but it's a bit backwards, all right? Which is very odd to think about. So we would expect, like, this is what the number should be in hexadecimal. It's a bunch of zeros and then 2A at the end, because that's the least significant bits there. This really is the number 42 in decimal when you do the conversion. But when we break up our numbers into their corresponding bytes, because it's a 4-byte thing, it's not going to hold these addresses. These addresses are not going to hold those exact bytes. All right, it's weird to think about. It has to do with a concept called endianness, which is a fun word. Okay, so the obvious answer is like, all right, we're going to store 42. It's got 6 zeros and then it's 2A. We're going to store it in that order for those addresses. So this is our number. We're going to store it in this exact order as we would write it down on a piece of paper. This would go in address 100, this would go in address 101, 102, 103, and this is called storing the number in big endian format, all right? Where the most significant bytes, the one that packs the most punch, because this would be would make a large number if there was FF right here, right? Those would come first in a big endian format, and so this is the smallest, least significant bits coming at the last possible address, all right? Unfortunately, though, everybody decided that that's not cool enough, and so secretly, our computers, all the ones that we're using these days, Intel machines, ARM machines, they're storing their numbers in what's called little endian mode, where the least significant bytes come first. And so really, 42 is stored still as a chunk of 4 bytes, 4 separate bytes, but in opposite order. So it's storing it as 2A, 00, 00, 00, 00, all right? Which is very weird to think about, all right? So let me prove that to you. It's going to look backwards, all right? Let me prove that to you in a file, all right? Let's say we have this number, a bigger number, 1,208 or 1287 in hexadecimal land, whatever that is. What is that? Zero x that. So it's that number, whatever that is. This would be stored as, right? It's really 00. If this was an int, it would store like that. You'd have the padding with the zeros, but it's going to be stored in memory in little endian format, so it would go in bytes 87120000. Isn't that weird? All right, it's a 4-byte number. Each byte it's chunked in terms of bytes, and so it's like you're making the number look different, but the computer understands this. You see these interpreted as an int corresponds to this number, okay, in hex at least. That's so crazy. So let me just show you that really quickly. I'll put this in a C++ file called bitwise, because eventually we're going to talk about bitwise operators. So let's say I have this number, int, I don't know, int y equals 0x1287. And I'll just call it like num or something. All right, that's my number. It's that in hexadecimal. Let's use GDB to see this stored in little endian. It'll be great. All right, so I'll compile this with the -G, and I'll run it in GDB. But I'll set a breakpoint after that number has been made. So let's set a breakpoint on the only other line, so the return 0 line. Let's break bitwise.cpp line 7, please. And so I'll run until there. And so I have my number now, right? It exists. I can say print num, or just p num. Oh, sorry, not $. I can just say print num. It's a normal variable. And so that's it in decimal now, or just p num, that exists. If I want to examine its memory, I can say examine the memory, like 10 hexadecimal things starting at address of num. You will see it's there in order, but I guess by default it's showing you in a pretty way. Let me show us as bytes, 10 bytes. There we go. Perfect. And so here is, starting at the address of num, it goes 87120000. It's exactly what we expect. Even though the number is 1287, it's being stored in little endian mode. So this byte is being stored first, then this byte, and then the other zeros that were necessary. Isn't that crazy? That's wild to think about, but blew my mind. Makes no sense, but it's how CPUs work these days for reasons. I can tell you more in office hours if you'd like. I have a theory for why we do it this way. So yeah, that's endianness. Weird. We also have types, right? That we should already remember. Hopefully, their size. So int, as I've been screaming about, that's 4 bytes wide. Every integer in C++ or C. Everything that's a char, every character value is taking up 1 byte. Floats take up exactly 4 bytes, so just like an int, but it's holding decimal numbers in a cool, fancy way. And then doubles are double the size of floats, and so they're 8 bytes. All right. So I haven't shown you how floats and doubles look in memory. They're encoded in a very special format that the CPU can understand still. They look nothing like these numbers. All right. 42 does not look like anything like this in as a float or as a double. 42.0 at least. All right. So that's something we'll talk about later. All right, not now. So, but yeah, I've shown you how to like convert into integers and stuff like that. Chars are still numbers; they just take up less space. Let me tell you how negative numbers work now, just in case you've never learned that yet. So, negative numbers. Let's first of all pretend that we're talking about chars right now, because I don't want to write a ton of zeros all over the place, because I want to talk about binary. Let's pretend that our numbers, like we're storing things in a char, and so we have 8-bit numbers. All right. What must the number -1 be as an 8-bit number? All right. Let's figure it out together. So whatever -1 is, you would agree, right, that if you added it to 1, you would get 0, right? Because that's the whole point of being -1. So let's start with the number that we know, 1. So if it's 8 bytes long and it's the number 1, it looks like that. All zeros, so this is binary. The number 1. Whatever, right? Whatever goes here, whatever is -1, should add to 1 and produce all zeros. 8 zeros, right? Because -1 plus 1 should be 0. Okay? So whatever -1 is, let's figure it out now in binary. So what must go here? What digit must go here to produce a 0 down here? It definitely can't be a 0. You see that? Because that would force a 1 here. So that's no good. So we must put a 1 here. Whatever -1 is, as an 8-bit number, as a char, it must have its rightmost bit be a 1. And that's going to force a carry, right? 1 plus 1 is 1, 0. We've carried here now. And now we got to figure out what digit goes here for -1. What bit goes here? Well, again, I can't put a 0 because that would put a 1 down here. So again, I'm forced to put a 1 here. And the answer is 1, 0. Perfect. And for a similar reason, right, I can't put a 0 here because that would force a 1 in that position. I need to, again, put a 1. Force the carry. All right, and I think you can imagine what's going to happen now. Put another 1 here, carry, because of the carry. Another 1, carry, 1, carry, 1, carry. 1, we get our 0 finally at the end. And we actually have 1 more carry. This 1 comes out here, but we have no room for that 1 anywhere. We only have 8-bit numbers, so that like this would be the 9th bit. It's going nowhere. All right, this is called a carry out. All right, this is a carry out of our most significant bit. MSB for short. Okay, and so we have nowhere to put it, so it just like vanishes. But the CPU can see it. We have flags for that, for example. But we end up with the number 0, and so that means all 8 bits that are all 1s, if we're talking about 8-bit numbers at least, that is the number -1. And so as an int, it would be 32 1s. 32 1 bits is -1. -1 in binary is all 1s for whatever width we're talking about. All right. Same for -2. We can figure out what -2 must be. Well, whatever it is, it's the number that, when added in binary to the number 2, produces 0. So let's play that game again. I'll go a bit faster this time. So okay, let me leave myself some more room. All right, if I want a 0 here, I can't put a 1. So for 1, so I can put a 0. So that must be the rightmost bit of -2. And then for the same reason, it just kind of looks like 1 again now from here on. Now I'm forced to put a 1, make it carry, forced to put 1, make it carry, because I can't put a 0 here, that would force a 1 here. So I gotta put a 1, make it carry, all over the place until we're done, and we have again that carry out at the most significant bit. Boop. And it vanishes. So this, all 1s and then a 0 at the very end, that is our -2. Alright? That's the secret. And so analytically, that's how you can figure it out and like understand it. But there's a faster process, of course. So if you would like to negate a number, what we are doing with the way that we're storing our numbers, the reason it works like this, we're calling our numbers, or we're using what's called the 2's complement format. All right, that's the encoding of negative numbers that we're using inside of the computer. And there's a quick way to take a number and negate it using 2's complement. All it is you flip all the bits of your number and then add 1. Okay, that's going to do 2's complement, and that will negate a number. It'll take a negative number and make it positive again, or take a positive number and negate it and make it negative. All right. So for example, if I wanted to produce the number -1 and I didn't know that this was the answer, I would start with +1, as 8 bits, of course. If we're talking about 8-bit numbers, I would flip all the bits. I'll use tilde to represent that because it's a bitwise operator in C++ that I'll show you soon. And that would produce, if I flip all the bits from 0 to 1 and 1 to 0, I get that, right? Flipping all the bits. And then you add 1. Well, there's room in that rightmost bit for 1 more, and so that would be my +1. And you can do the same thing again to negate it right back to +1. Because if you flip all the bits, you get 0, you add 1, you're back at 1. So it works in both directions for any binary number. Okay? So, yeah. Also, another key thing to think about is we're kind of giving up half of our numbers to store negative numbers. Okay? Because this, as an unsigned char, is the biggest possible byte value, which is 255. We have given up the number 255 for -1. I hope that makes sense. Where we've like given up half of our numbers, and the way that we know if our signed number is a negative number or not, we could look at the most significant bit. That corresponds to it. If you see a 0, that means your number is meant to be a positive number and interpreted as such. If you see a 1, it's meant to be interpreted as a negative number. And so that's why -2 and -1, they have a 1 in their most significant bit. That's showing you that it is a negative number. All right, we've given up half of our numbers, half of our large numbers, because we want to store negatives too. All right, and so 0, of course, in the most significant bit, is going to represent that numbers that comes after is meant to mean a positive number, okay, as usual. So that's the difference between signed and unsigned numbers. We're allowing that most significant bit to mean negative, okay? So you have integers, those are allowed to be negative, versus unsigned integers. Those let you have those big numbers at the expense of not having negative numbers at all. So you don't have any signs possible in unsigned its. It's only positive numbers. And so there's chars, and then there's unsigned chars. Chars can be negative. Okay? So, with that, I think I'd like to give you a question for you to try. All right? So here's your question. Assume that we're working with 8-bit numbers. So every number is 1 byte long. We're working with chars. I'd like you to take this number, represented in hexadecimal, and negate it using 2's complement, so flip all the bits and add 1, and write it in hex again. Okay? You're going to have to go through binary. So you don't even have to go to decimal, though. I don't know what 1b is in decimal unless I do some math, but I can immediately convert this to binary because you don't even have to work from the rightmost digits. Like the 1 is 4 bits, 0001. The b is 4 bits. That is 11, right? So that's going to be 8 plus, not 4, plus 2 plus 1. And then to negate it, using 2's complement, I'm going to flip all the bits. So 1, 1, 1, 0, 0, 1, 0, 0. And then I'm going to add 1. And there's room in that bit at the end for a 1, so I can just place it there and not have to do too much extra thought. 0, 1, that's my answer. And now I need to convert this to hex. So I chunk it up into 4 bits. and this is 5, and this is not quite 15, it's 14. And so that's 1 before F, it's E. So this is E, this is 5. And so E5 is the number in base 16 that is the negated form of this, and you can see that this was originally a positive number because it has 0 there, and this is now a negative number because it has a 1 there. We're interpreting it as a negative number. It's not whatever E5 is when you do the expansion. It is meant to be interpreted as a negative number, okay? And so it's negative this, whatever that was, negative 27. All right. So yeah, let me just do a completely different thing for a split second and talk a little bit about C strings, because that's going to be important in the C language later. So C strings are the stuff that you put between two quotes. So a string in the C language is stuff that you put between two quotes. It's really just a char array. Actually, in C++, this is still a C string. It's getting converted to a string if you use the string type, though. So you can store that as, like, this would be the type of that, char C bracket bracket. All right. So that is, it's just a secret array of characters. All right. It looks like this in memory. So every character takes up a byte. So you got the B character, a byte for the L character, or a byte for the A character, a byte for the H character. And then, though, no arrays in C++ or C know their size. So C strings need to mark the end of the array because they don't know their size. And so you have this special null terminator character. That's how you know when you're at the end of your C string. Okay? So this will be important later, but it kind of ties into what we're doing here because each of these takes up a single byte. Each character takes up a single byte, and every character has a certain ASCII code for it, a certain number that represents it. Okay? So yeah, I think, for the rest of this lecture, we're going to talk about bitwise operators now, and bitwise operations. And this is going to get us some more practice with binary and like flipping bits and doing cool stuff. All right, so this is code now. All right, I'm going to teach you how to mess with bits in code. All right, so there are a bunch of different bitwise operations that kind of correspond to the logical operations that we know and love. They act on individual bits of numbers, though, but we interpret like the ones as true and the zeros as false. We just kind of line them up. All right, so the AND bitwise operator, instead of the logical operator, which is 2 ampersands, is just a single ampersand. So AND is good for extracting bits. The OR bitwise operator, which is a single pipe character rather than 2 pipe characters, sets a bit. I'll show you that in a second. And then the bitwise NOT, or bitwise negation, it flips all the bits of a single number. Okay, so let me show you an example of each of those, and then I'll show you how they work in code and like what they're good for. So what do I want to do? Let me just show you each of these. So the idea is you have numbers in C++ stored normally, but if you ever like perform the ampersand operation, that's going to give you the bitwise AND on those numbers. All right, so let's say we have the numbers, I'm going to use binary right now, but assume they're stored inside of C++ in variables. Like we have a variable that holds this in binary, 1011, and we have a variable that holds 1101 in binary. You can give both of those variables and put an ampersand in between them, and C++ will do the bitwise AND of those two numbers. And so the way it works is it interprets 1 as true and 0 as false, and it lines them up, each corresponding bit, and it performs logical AND on each of those bits. All right, so this, we have a 1 here and a 1 here. So it's going to do logical AND on both of those numbers, interpreting them as both as true. So it's going to do true ANDed with true. What's the answer? True ANDed with true is still true. Perfect. That's how that works. So it's going to produce a new number with some new bits corresponding. All right, and that's going to do these guys. It's going to line them up and do logical AND because we're doing bitwise AND. So all right, what's true ANDed with false? Well, that's going to be false. So 0 is going to be placed here in the resulting number. It produces a number. And then again, false ANDed with true is still false. And one more, we have true ANDed with true is true. And so AND is good for extracting the bits of a number. Let's say we want to extract, like we have this number, and we'd like to extract this digit. Oh, sorry, I want to be in a different color. I'd like to extract this digit. I don't care about this digit, but I want to extract these other two digits. All right. So the way you do that is you put a 1 in the bit positions that you want to extract of the other number, and you put a 0 where you don't care, and watch what happens. Do you see how when you AND with a 1 and it was a 1, it preserves the 1? All right, so it takes it and it moves it on down. It takes the 1, 0 and it moves it on down. Again, because like, all right, if there's a 1 there, the 0 is going to force the 0, which is what we want in this case. And then if there was a 1, though, it would place a 1 in the correct position. So it's kind of bringing them down, all right? So it's extracting just the digits we care about. And it's like clearing this one out to a 0, okay? Clearing that one out to a 0, kind of. That's how you think of it. So that's how that works. That's bitwise AND. Bitwise OR is very similar, but it's going to do the OR operation on the bits. So if we have 1, 0, 1, 1, and let's say 1, 1, 0, 1, you can do bitwise OR on that. That's a single pipe character. It's not a 1. And it produces the following. It produces another number again. It's going to do logical AND on each bit as it lines up them. All right. So this is a logical OR. True ORed with true, that's still true. So a 1 goes there. True ORed with false is still true. So a 1 goes there. False ORed with true, true. And then true ORed with true is still true. So we got all 1s here. And what OR is good at doing is setting bits. You start with your number and you're like, I want to make sure I keep this number, and then I also would like to set, if those bits aren't already set, I want to set these particular bits. You put a 1 in the bits you want to set, and a 0 where you just want to preserve and you don't care what it was before. So do you see how even if there was a 0 before, it has now been turned into a 1? All right? So it's forcing these bits to turn on, essentially, and then the rest are getting preserved. Like the 1 just comes down because it was a 1. It would have, if it was a 0, it would have come down as a 0. So that's what bitwise OR is good for. And then bitwise NOT, or negation, is, or complement even, is flipping all the bits. So assuming we had 4-bit numbers only, 1, 0, 1, 1, tilde on just that, flips all the bits of it and it turns it into 0, 0, 1, 0, 0. All right? That's bitwise NOT. And if this was like an integer, you could imagine like there's 32 bits and these are all zeros. So they'd all turn into a bunch of 1s. Okay? So that's the idea there. So yeah, let me give you some examples in actual code with this in C++. Let's start with this number in binary, 1, 0, 1, 0, 1, whatever that is. I'll put that into a variable. Boop. So I've got num already. Let's make a new variable called just x, I guess. And I'll store a binary number. So 0b, whatever this is, 0, 1, 0, 1, 0, 1. All right, that's my number. Let's see what it is. See out x. So g++. Oops. Boop. Compile it. I can actually run it now because it's going to print something. And apparently that's number 21. And let's say I'd like to extract bit 2 of this number. First of all, the numbering for bits works like this. The rightmost bit is bit number 0. This is bit number 1, and so it's bit number 2. I want to figure out, was this a 1 or not? I want to extract it. All right? So I like to extract this bit, and the way we're going to do it is with an AND operation. Okay? If I want to extract bit 2 of a number, what do I need to do? So like, regardless of my number, I would like to extract whatever is in bit 2 position. So I'm going to put a 1, I really, really care about this bit right here. I'm going to put a 1 in that number, in that position, and a 0 everywhere else, and I'm going to do a bitwise AND. Because, do you see how it's going to 0 out everything else, and if this number was a 1, I'll get a 1. If that number was a 0, I'll get a 0. And so I can check and see if this bit was set by checking if the result was all zeros or not. So if it was the number 0, then it wasn't set. If it was something other than 0, that means there was a 1 here, which means there was a 1 up here. You see that? That's how you check if a bit was set. So I'm going to AND with this number, which is the number 4. Right, so I can bitwise AND with the number 4. So extract bit 2, I'm going to AND with the number 4. Honestly, you don't even have to figure out that it's the number 4. You can just be like, all right, I'm going to AND with 0B 0100, something like that. Yeah? You don't have to do any extra thought if you don't want to. But here's how you check if bit 2 is set. All right, so if I do X, I bitwise AND it with 4, and the result was non-zero. Right? That would mean that there was a 1 here because it would have preserved the 1. If there was a 0 here, the whole thing would be 0. Right? If it's non-zero, that means that that bit was set because everything else is being zeroed out. That's the only thing we're zooming in on right now. So we can see out bit 2 was set. All right? And it was, wasn't it? 0, 1, 2. So we're going to get the 1 there. It'll produce the number 4, essentially. And we will see an answer there. We will see that it was set. So that's pretty cool. Let me show you how to set now. Set bit 5 of the number. So here is, where's bit 5? It's 0, 1, 2, 3, 4, 5. So the bit 5 is not currently set in this number. We're going to make it set to a 1 using bitwise OR. So regardless of what your number is, like bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, I want to make sure this bit is set, regardless of what it is. So I'm going to bitwise OR with a number that preserves everything else. So zeros everywhere but the one I want to make sure is set. And I put a 1 in the place I want to make sure is set. All right, because all the zeros will just preserve what was there. If it was a 1, the answer is a 1. If it was a 0, the answer is a 0. It'll preserve it. So I'm just going to put X to mean that. But it's going to force a 1 in this position because if you OR with true, the answer is always true. That'll force a 1 in the place we care about putting a 1. Okay? So to set bit 5, I'm going to bitwise OR with that number. Set bit 5, which means OR with a number with a 1 in the 5th bit position. Which I think is that 0, 1, 2, 3, 4, 5. That one. Whatever that number is. And you can check what it is. It's 2 to the 0, 1, 2, 3, 4, 5. So 2 to the 5th power is 2, 4, 8, 16, 32. It's really the number 32. But you don't even have to think about that. Just like that's the number I care about. So X equals X ORed with this thing. Or 32. Either one works. Okay? And then that will force that bit to be set. And that's actually going to change our X. So X was 21. That bit 5 was not already set, so it's going to add 32 to the number, essentially. 21 plus 32 is apparently 53. Cool. So there's that. Let me show you that really deep down the computer really is using 2's complement to store negative numbers. Let's negate the number using the 2's complement algorithm rather than like multiplying by -1 or something. Let's flip all the bits and add 1. All right, so let's negate using 2's complement. I'll flip all the bits with the tilde to do the negation, and then I'll add 1 with the plus, as usual. So this will be cool. We're going to arithmetically negate the number to be the negative version of what it was. So let's negate using tilde and plus 2's complement form. So obviously you could totally do this, like x equals x times -1 to make it the negative version of that number. You could even do this. You could be like -x. But we're going to do it the old-fashioned way, the way that the CPU is really thinking about doing it, secretly. So we're going to flip all the bits of x and then add 1, and that will create the negative version of it. So if I print it out again, we'll see -53, because that's how it's encoded. That's how it works. There's my -53 being printed out now. Nice. Let's see, what else do I want to do? Let me see, do I want to fast forward right now? Not quite, I don't think. Maybe not, actually. All right, let's do something more complicated after I teach you new things, though. I want to show you assembly first. Yeah, let's go to assembly first. So here is the corresponding operations in assembly. There's an AND instruction, there's an OR instruction, but apparently they wanted to make it 3 letters long, so it's OR with an extra R for bitwise OR. And then to do the complement, it's actually, sorry, I can't remember if it's the complement or not. Let me check my notes really quick. That's either the complement or arithmetic negation. Dun, dun, dun. Okay, yeah. No, this is going to be the complement, MVN. It's going to bitwise negate. That's what that means. So move negated is kind of what that stands for. All right. So let me show that to you in assembly before we go any further. So I'm going to make a new assembly file, and I guess I want to just steal stuff from last time because I don't want to reinvent the wheel. Let's look at a file from last time. Lecture 4. What do we got in assembly? Branches? Sure. Boop. So let's steal most of that. Everything and the exiting. And then we don't need anything in the data section. So here's a good start of a program. And yeah, so let's do exactly kind of what we did in C++. Let's get the C++ on the other side, maybe. We started with this number, which was 21. So let's get that in a register. So I'll move into x0, let's say 21, and let's extract bit 2 into, let's do it in x1, let's say. So move, extract bit 2 with the AND, of course. So we're going to do the AND operation right now, AND instruction. So let's first get the number we want to add with, or AND with, in a register. So 4 needs to go somewhere. So move into x1, the number 4. And now I can AND into x2, let's say, x0 and x1. Okay, so that'll be that one. And then you kind of want to just you can do a branch now to check if x2 is equal to 0. If so, you can print stuff out, ... That would take too much extra time, but I know you can do that. And then let me show you OR. So let's set bit 5 with an OR instruction. It's 2 R's for a weird reason. Or like a pirate, I guess. So alright, we're gonna take x and we're gonna, or x0, and OR it with the number 32. So let's get 32 somewhere. Move into x1, 32 now. And I will OR the answer, OR into x3, that's a free one, x0 and x1. And then let's do the negation with the 2's complement. So what this will do is, well, we got to take our x0, we have to flip all its bits. That's the MVN instruction. It stands for move negated, all right? Bitwise negated, not arithmetically negated. So MVN, let's do it into x4, let's say. Just x0. So it takes x0, what it was, and it flips all the bits and puts that in x4. And then we want to add 1 to that. So add x4, x4, 1. And that should produce the negative version of 21. Okay? That's how that'll work. 21 still, because we're placing all these ands and ors in new places rather than overwriting like I did here. Okay? So, and then of course we exit. So those are the ideas. Those are bitwise operations now in assembly. Those exist. So let me show that to you with, I guess, GDB .s-o bitwise .o, or sorry, I need AS first, excuse me. Then ld-g bitwise.o into bitwise, overwrite the old one. And now I will gdb bitwise and set a breakpoint on, let's set a breakpoint on line 19 after we've done all this stuff. So break, oops, is it not getting my input? There it goes. Bitwise.s line 19, please. And I like to run the program until there. Cool. So let's take a look at what we see. So is x2 a non-zero number? Print x2. It sure is. Oh, sorry, x2, excuse me. x2 is a non-zero number, yay, 4. So that means the bit was set. So x, first of all, x0 is 21, right? x0 is 21, we never changed that. x1 is 32, and we're ORing that's bit 5 set. So we're ORing into x3, x0 with x1, bitwise OR. So printing x3, we should see 21 plus the 32 from that new bit that we're adding, because it wasn't already set. So it's 53. Right? If it was already set, it's not going to touch it. It's just going to preserve it. But the ORing makes sure that it was set, that bit. And then x4, with this process, we negated it. And I already accidentally printed it out, but there it is. We get negative 21 to our positive 21. That's the secret. All right? So that is bitwise stuff in assembly. And there's more. There's more bitwise operations that I want to show you. I guess we'll go back to C++ for that. Or even I can just show it to you without going to code, I guess. I want to teach you exclusive OR, at least on a slide. That is a new kind of bitwise operation. It's the caret character in C or C++. You remember when you were like a CSCI 40 student, you thought this like meant one thing to the power of another thing, and it gave you a really weird answer when you tried it? Well, this is why. It's going to do a weird bitwise operation. And exclusive OR, it's going to do logical exclusive OR on the corresponding bits of two numbers. So the way it works, the way logical exclusive OR works is like this. Here is A exclusive OR with B, where A and B are individual bits, true and false. So true, 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 false, false, true. Here's the truth table, false, false. Here's what exclusive OR does on a single bit. True exclusive OR with true, that is false. False exclusive OR with false is false. These guys, though, where there's just one true, it's true. So it's like normal OR, but it doesn't like it when they're both true. It has to be one or the other must be true exclusively. That's what it means. So it's like OR, but this is a false instead of a true. Okay. So exclusive OR works like this: 1 0 1 1. Exclusive OR with a number. It's going to do the corresponding logical exclusive OR on each bit. And exclusive OR is good for toggling bits. So the way that you toggle a bit is like, let's say that I care about toggling this bit right here. And so I'm going to exclusive OR with a number with a 1 right there and a 0 everywhere else. And let's watch what that does. So 1 exclusive OR with 0, true exclusive OR with false. They disagree, so it's a 1 for true. These are the same, so it's false. Same, so it's false. And different, so it's true. True exclusive OR with false is true. So that's the answer. And these zeros preserve what was there. So the 1 0 got preserved down here, the 1 got preserved down here, and the 1 in the position we cared about toggling toggled this bit. Because do you see, because it's a 1, it became a 0. And if it was a 0, now it would be different. It would have become a 1. That's kind of cool. So yeah, it's the caret character in C++. I can just assume you understand that. We don't have to go to code for that. So that's that one, exclusive OR, good for toggling bits. And yeah, the last ones I want to show you are shifting. All right, there's shifting, and there's also rotating. There's no C++ for that. It's like you got to break it up into shifts and ORs, but there is an assembly for it. So let me teach you those. So left shift, this is where like the cin and cout operators really came from. They're really shift bitwise operations that got overloaded because they aren't used as often as other things. Cout and cin kind of took over. So shift left, bitwise shift left looks like this. Two less than symbols, and that's going to take a number. So like you start with a number on the left side. Let me write in binary just for fun. You can left shift that by a number of bits. So let's left shift it by 2 bits. And what that does is it produces another number. Oh, sorry. Why did I write a 2 here? Excuse me. Let me fix that. Well, that's not binary. There we go. So like that's my binary number. I can left shift it by 2, and what that does is it kind of like shifts every bit over 2 positions, 2 over, to the left. And so it shifts all these guys over, and it brings in 2 new zeros, 2 fresh zeros. So it takes what there was before, if there's room at least, 1 0 1, and it adds 2 fresh zeros at the end of it. All right. If you think about that, what it's doing is it's multiplying by 2 to the nth power. So like this has just multiplied by 4. By 2 squared, because it adds a new number, right? Because like here's 1, add a 0, it becomes in binary. 2, add another 0, now it's 4. You're multiplying by 2 every time you add a 0. So that's left shift. And then right shift is similar. It's going to move bits to the right, okay? So let's say I start with this number 0, 1, 0, 1. I can right shift it by 1 bit, and it will just like move everything over. And this guy needs to be chopped off now, right? So it's going to chop off this bit and produce just like 0, 1, 0. And that divides by 2 to the nth power, okay? So, how do I want to show that to you? Yeah, there's actually two different kinds of right shifts though. Left shift always brings in zeros. Right shift sometimes brings in zeros, sometimes brings in 1 on the left. All right, because you have bits over here too. Like you got to bring in a fresh one. It's either a 0 or 1 when you're right shifting. So there's either logical right shifting or arithmetic right shifting, and it depends on the type that you're shifting. Sorry, how do I want to explain this? The one you get depends on the type of the variable that is on the left side of your shift. That's what I mean. All right, so if you have an unsigned number, it's going to be a logical shift right. This is the corresponding assembly instruction. So this is logical shift left, logical shift right. Those are your assembly instructions that do this. You can look them up on the documentation. And then there's also an arithmetic shift right for signed numbers. ASR is what that's short for. So right shift, you get the logical kind that brings in zeros always when it's unsigned. If you have a signed number, you're getting arithmetic shift right, and that's going to bring in a 0 if it was positive and a 1 if it was negative. So let's pretend we're working with chars, signed chars, and I have this giant number. Okay, I have this giant number, and it's meant to be a negative number, and so I'm going to shift it right by 1. The arithmetic shift right works like this, right? It's going to chop off this decimal place, and it has to bring a new decimal place in to go over here now, and it's going to bring in whatever that bit was, so it's going to keep it a 1 there. Okay, that's kind of the idea. So that's kind of how arithmetic shift right works. It kind of keeps things negative if they were negative and positive if they were positive. That's a lot of words. You don't have to really worry about that in this class, but at least you've heard me say it in case you need it later. So let me just show you an example of like shifting and like using cool ideas that are on this slide and previous slides. So let's say we've got a number, and I would like to extract bits 2 through 5 of that number. Okay, 2 through 5. What does that mean? I'll use and I will also use left shift to do it. All right, so I want to extract bits 2 through 5 of some number. Let me make that happen for us. If it's 8 bits, I guess I have to convert. I guess I have to make an 8-bit number. So let's start with x. So char x or char char y equals whatever x was. Convert it down to 8 bits wide. So chars are 8 bits. And I'd like to extract. Let's extract bits 2 through 5 from y. All right. And so what does that mean? How do we do that in using bitwise operations? We're going to and, right? We're going to do y ANDed with this binary number with 0b 3, 4, 5, 6, 7, 8. Here's a bunch of zeros. 4, 5, 6, 7, 8, and I want 2 through 5. So I'm going to and with a bit, and with the number where bits 2 through 5 are set. So 1 there, 3, 4, 5 with that number. That's what's going to happen. Okay. And an easy way to get this number, if you want to move things over quickly, it's just like it's 1, 1, 1, 1 shifted left by 2 bits. You see that? So that's one way to compute it. So cout y ANDed with 1, 1, 1, 1. If you didn't feel like writing a bunch of zeros, this is useful when you have larger bit positions that you care about. But you can just shift that left by 2, and do you see how that will produce this number? 1, 1, 1, 1, 0, 0, because it'll bring in 2 zeros because you're shifting left. Isn't that cool? So yeah, let's extract those bits and see what happens. Cool. And so apparently the number turned into 8. Okay, that's how that works. If you want to extract just a single bit, just bit 2, like again, shifting is a great thing to think about because you don't even have to worry. You can just be like, you could and with just start with 1, that's the number with bit 0 set, and shift it left by 2. That will give you a number with just bit 2 set. Isn't that cool? That's pretty useful. Alright, so that's what I wanted to say there. And there's also rotating. This, there's not just one operation for that in C++ or C, but there is an assembly. If you would like to rotate the bits of a number, you can use ROR, and it's going to rotate the bits of a number in a register. Let's pretend our registers were only 8 bits wide, because I don't want to write a bunch of bits down. Let's pretend we had a register that held just this, and our register was only 8 bits wide. That's all it held. To rotate right by a certain number of bits, this is how it works. Like, if I rotate this number right once by 1 bit, it's going to rotate every bit right. This is what will happen. Right, 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 right. And then this guy, there's nowhere to the right, so it goes and swaps places, and it moves to the left. All right, so this turns into 0, 1, 0, 1, 1, 0, 1, 1. I hope that makes sense. That's how you rotate the bits of a number. And you can do that more than just once. All right, so if you're in C or C++ and you want to rotate your numbers, you have to you got to shift over and get everything that was on the right and move it over to the left. It gets a little complicated. There is no 1 bitwise operation in C++ that does the rotation. You have to combine what we know to make that happen. Okay, so that is the secret, and that's one reason to learn assembly, I guess. So yeah, let me give you one last question on this stuff, and then we'll call it a day. So let's say that we've got a number in x1. Let's say we got the number 15 in x1. And I'd like you to place 61, all right? 61 in x0, all right? Using x1, of course, using only bitwise operations. So the ones that you're going to need are LSL and OR. The way that LSL works is you say, I'd like to logically shift left a number in a register, so like x. I want to put the answer here, so like xd, that's my destination register. I want to put the answer here, and I want to use this register, and I want to shift it left by this amount, n. Okay, I hope that makes sense. That's how you use LSL. And then OR I showed you already. OR is destination and the 2 registers you want to OR together. Okay, you could technically OR with an immediate right here as well. So yeah, how do you do it? See if you can figure it out. All right, I claim that's all you need. So what is 15? If 15 is an x1 right now, what does it look like? 15 in base 10. What is it in binary? It's just all ones. It's 4 ones. Okay, and then 61 in decimal. What is that in binary? You'll have to do some extra math, but it is this. It's 1, 1, 1, 1, 0, 1, base 2. All right, I promise. So how can we turn this into this? Do you see how it's kind of the same? If we do this, if we start with this, do you see how if we left shifted it, 1, 1, 1, 1, if we took that and we shifted it left by 2, we would get 1, 1, 1, 1, 0, 0. And then we just need to make that last bit a 1, bit 0 a 1. So we'd OR with the number 1, because that would put a 1 in that bit position. We get 1, 1, 1, 1, 0, 1. So that's what we need to do, okay? And yeah, another way to think about that is we need to 15, we need to multiply it by 4, right? Because that's left shifting by 2. That gives me 60. If I just add 1 more, that'll give me 61, and I can get that by just putting a 1 in that position, all right? That's another way to think about it. So yeah, if 15 is an x1, how do I get from here to here? Let's put my answer in x0. So it's logical shift left into x0, starting with x1, and I want to shift it left by 2, placing the answer. So now I've got this in x0. Then I want to OR what's there. OR with 2 R's, whatever is in x0, itself by the number 1. There. And so those would be your 2 instructions to achieve your goal, all right, using bitwise operations. So yeah, I think that is all that I wanted to say for lecture today. We're going to come back and continue, of course. We've got a little bit more to talk about with these slides, but we'll save that for next time. I do want to release your first homework 0 right now. and I'll give you a couple weeks to work on it. So go check the due date on Canvas. It is whatever it says there, but here is your homework 0. This is what you'll be turning in. Right? You'll be turning in like a PDF of your answers. Make sure that they're legible, please. So like, here are all of your questions, and here's what I want you to practice. So practice adding some binary numbers, practice adding some hexadecimal numbers, doing some base conversions, doing some shifts and things, and like thinking about the corresponding assembly, all the stuff that we were talking about today. And yeah, you can also do this kind of stuff on W registers. So here are some examples of you being forced to do that. Remember that the bitwise negation is going to be MVN. That will negate something, and so you can go check the code from class for that as well. And yeah, just going in back in between binary and decimal and doing these bitwise operations and getting some experience. So that will be your 0th homework assignment, and here is how I grade homeworks. All right, I'm pretty lenient when it comes to grading homework. So I will give you, because I know that homeworks, right, they're meant to be practice. It's not a test yet, so it's okay to get some things wrong, but please try. So I'll give you, I promise to give you full credit to your homeworks if you get at least 70% of the questions correct, and you made an effort on every part of every question, and I can tell that you made a serious effort. All right, if you just write random answers, then I'm not giving you credit, right? Because that doesn't show that you made an effort. Show your work if you want partial credit and you think you got it wrong. Okay, so that's my promise to you. If you show me that you made an effort and you get most of them right still, I'll give you 100%. All right, I will give you a C on your homework, 75%, if you got at least half right and you made an effort on most questions. Okay, and I get to break ties, all right, as the instructor. I get to use my judgment and give you a 75% if I think you made an effort on most questions. And then I will give you a 0 though for anything less than that, because then it's not worth me looking at your assignment. All right, you didn't do much at all. So if you got less than 50% correct, or you didn't make an effort on several questions, you either should have come to office hours or the tutorial center to get help and get more correct, or you just did everything quickly and you didn't try. All right, and so I'll give you a 0 in that case. But it should not be hard to get 100. Just keep that in mind. All right, that's how I'm going to grade the homeworks. And so yeah, take a while to work on that. Hopefully it helps as you're practicing and getting everything stuck in your brain. And we will come back next time and finish up these slides and also start some new ones. So I'll see you then.